Today we are going to be doing a statistics paper. I just made myself a hot drink. Now statistics ain't my favourite thing to do in my pastime, but I figured if I'm going to do a lot of different papers from CIE and work through them all, I might as well start off with this trash statistics. Nah, it's just alright. It's not too shabby. My plan is to basically go through a lot of CIE papers and just work through them. It's been a while since I've done any of this, but I'm sure I can do it. I had a quick geese through this paper. Pretty sure I can do most of it. So we should be good. Right, let's crack in. So our first question, question 1, says the lengths in meters of cars are in a city are normally distributed with a mean of mu, so mu, which we don't know, and a standard deviation. So this is cut off, but I looked at it before. You got a standard deviation of 0.714, and the probability. This also says that the probability of a randomly chosen car which has a length of more than 3.2 meters, 2 meters, and less than mu meters is equal to 0.475. So then it asks us, what is mu? What is it? Do you know? I think I do. So let's have a look here. So we've got a normal distribution. So first off, let's just draw that out so we can see what we're working with. You can see my shitty normal distribution. Actually not too bad. And we've got 3.2 here, and then mu here. And the area, which I hope you know, the area under this graph is the probability. So this is 0.475. And basically, I'm just going to go through this and just tell you what I'm thinking. So immediately I'm thinking that, well, mu, what's an equation I know, is that for a standardized normal distribution, we can transition from a real life situation, so this with 3.2 and a mu we don't know and a standard deviation we know, to a standardized normal distribution through this equation here. So I'm thinking that right now. I'm thinking that could be a good path. So we find the z value for 3.2 in the normal standardized normal distribution, then we can find the mu. So because this is symmetric, we can then say that this little bad boy in here is 0.025, and yeah, so then we could go like this. And we can say, well, because it's symmetric, let's just flip it, and we can say, because when you look at your standardized normal distribution table, which I'm pretty sure you're given, if I'm not wrong, I put it in here, yep, you can see on this that it takes the z value and then the area to the left, so this thing here. So if we go back onto our test, so this is going to be 3.2 plus mu. I mean, it's kind of irrelevant, but just making sure. And this area here, well, this is just going to be 1 minus 0.025, which is equal to 0.975, right? Cool. So we have, now from that, we can find out, well, what's the z value of that probability? If we have this equal to 0.975, well then our z value is going to be, if we look it up on the table, which I can do, is going to be 0.975, where's that bubble? There. So it's going to be 1.96. So it's going to be 1.96. But then for 3.2, because it's on the opposite side, and remember for the normalized standard distribution, we have a mean of 0 and a standard deviation of 1, I'm pretty sure. So that means that our z value for the x value 3.2 in that situation is going to be negative 1.96, right? And it'll be like, you know, yeah, negative 1.96. That'll be 0. And then, so then from there, obviously, now we can use this. So we have negative, because we're relating the x and the z. 3.2 corresponds to the negative 1.96, and then we have a mu, and we know our standard deviation is this. And where's my calculator? So then we just calculate this, just times, and then so then it's going to be minus 3.2. So the answer will be, and I'll round it, will be our mu equals 4.6 meters. And that should be the answer. I'm pretty sure. Hopefully. Alright, cool. So, let's go on to the next one. I think I'm just going to bang out the entire thing. I mean, it's... Right. Okay, so question 2 here. So we have a table of dragonflies. Pretty cool creature. And they're giving the length of those dragonflies. So, state which class contains the upper quartile. Right, well, the upper quartile is just, I'm pretty sure it's just the medium of the upper half of a set of data points. So it's basically pretty much the 3/4 point. So we can find that pretty easily. I mean, we have, how many dragonflies do we have here? 8 plus 25 plus 28 plus 31 plus 12. 25, 31, so it's going to be 104 dragonflies. And then we want to know, well, we just times this by 3/4, right? And then we can know the 3/4 point. So that's the class it will contain. So if we just go, let's call it the upper quartile, it's just going to be 104 times 3/4. Which equals 104. Should probably have just figure this out in my head, but you know, that's why we got calculators, right? So it's the 78th point, and well, we can look here. So we've got 8 points there, and then we've got up to here. We've got 8 plus, so that's 33, and then up to here we have 51. Oh, 61, sorry. 61. Brain. So then it's going to be in here, right? So the 78th point exists in this range. So the answer is, which class contains? Well, the class is the 5.5 to 7.0. That's the answer. I just looked at this. Draw a histogram on graph paper. Yeah, I'm not going to do that one. You can do that. It's not too bad. I mean, it's just, you just need to learn how to draw a histogram. I can't really be bothered, to be honest. Okay. Right. Okay, right. I wonder how long this is. How long is the test? Like an hour and a half? Jason throws 2 fair dice. Numbers 1 to 6. Event A and event B. Okay, so we've got 2 events here. So we got, we've got event A, which means that one of the dice, so one of dice is divisible by 3, and the other, so one of dice, is not divisible by 3. And then we've got an event B, which is the product of the two numbers obtained is even. So the product of two dice numbers is even. Cool, and we're throwing two dice, so we could call it our sample set. We're going to have 1, 2, 3, 4, 5, 6 twice. So the total number of possibilities is going to be 6 times 6, right? You know, you have 1, 1, 1, 2, 2, 4. Like, you can write them all out if you want, but it's 6 times 6. So I determine. So let's just little, you know. So determine whether events A and B are independent. Right. Well, I wrote this down before, and so let's just do it like this. So the thing is, with a lot of the stuff that I can say here, you can look it up and it will make sense if you look it up. I'm not going to go through the justification of some of the equations that I bring up here. For example, this one, so I could say two events A and B are independent if and only if the probability of A times the probability of B equals the probability of A and B occurring. So that's what you've got to prove. And this equation comes from conditional probability, and you can really get some intuition there that the conditional probability, which is this equation, so over the probability of B, I'm pretty sure that's what it is. So this basically means here, this means what is the probability of A given that B occurs? And the intuition behind this independence formula of two events being independent of each other comes from this conditional probability. And you can, look that up and try and understand that yourself. But anyway, so in order to prove that these two events are independent, we need to show this equation is true. So what's the probability of A? Well, first let's look at what A could be. So the sample, the possible combinations. Well, this is one die is divisible by 3 and one die is not divisible by 3. Well, what's divisible by 3? 3 is divisible by 3. So you could have, and the other one's not divisible by 3, which is 1. So this is the first die, second die. And you could have 3, 2 is not divisible by 3. You could have 3, well, not 3, 3, because they're both divisible by 3. You can have 3, 4, and you can see what I'm doing here. 3, 5, and not 3, 6, obviously. You can have 6, so divisible by 3, not divisible by 3. 6, 1, 6, 2, not 6, 3, 6, 4, 6, 5, and not 6, 6. So that is all of the possible combinations to that. But also you've got to remember that we don't give a shit if it's what order it's in. So you could also have 1, 3, all of these in reverse, right? Oh shit. 4, 3, 5, 3. You could just times it by 2, but I'll just write them out. 1, 6, 2, 6, 4, 6, and 5, 6. Because you do a roll and it doesn't really matter what comes first and second. So therefore the probability, I need to get used to this pen, of A equals 1, 2, 3, 4, 5, 6, 7, 8, 16. 16 over the total, which is 36. So these are the possible outcomes of A divided by the total possible outcomes gives you the probability of A occurring. So 16 over 36 will be 4 over 9. So therefore the probability of A, because we'll probably do this later, is 4 over 9. Okay, let's keep this going. And now B, the product of the two is even. There's going to be a few more. So, well, let's just go through it again. Well, 1, 1, no. 1 times 1 is 1, which is not even. And then you can have 1, 2, which is even. 1, 3 is not. 1, 4. I'll just write them out. Why not? 1, 6. All the 2's, right? 2 times anything is even. 2, 3, 2, 4, a 2, 5, a 2, 6. And then you got a 3, 2, and a 3, 4, and 3, 6. And then you got a 4, 1, a 4, 2, a 4, 3. Look at me go. 4, 4, 4, 5, and a 4, 6. And then a 5, 2. And then a 5, 4, 5, 6. And then all the 6's. 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and 6, 6. Yeah. Gross. Okay, so what's the probability of B? Well, let's count those bad boys up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So it's 27. 27 over 36, which is, with my quick math, is 3/4. So therefore, the probability of B occurring is 3/4. And then finally, we've got to find this. So that is going to be, what is the probability of them both occurring? Well, we just got to look at the overlap. Well, let's look here. We've got 3, 1. Does 3, 1 occur here? No, of course it doesn't, sorry. 3, 2. 3, 2 occurs. 3, 2 occurs. 3, 4 occurs. With 3, 4. Oh my god, there's so many numbers on this page. 3, 4. 3, 5 doesn't. 6, 1 does. 6, 2 does. 6, 3, 6, 4, 6, 5. I'm just gonna go. Oh, yep. 2, 3 does. 4, 3 does. 5, 3 doesn't. 1, 6 does. 2, 6 does. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 12 out of 36. So this occurs 12 out of 36, which is a quarter, right? So therefore, the probability of A and B is a quarter. Okay, so finally, that we have, well, the probability is a quarter. Well, what's the probability of A times the probability of B? Well, this is going to be, what are they again? 4 over 9 times 3 over 4. 4 over 9 times 3 over 4, which is going to equal to 12 over 36, which is a quarter, which equals the probability of A union B. And therefore, events A and B are independent. Cool. I hope that makes sense. And in regards to the intuition behind what the fuck this shit means, I could go into it in these videos, but it would take longer if I went too deep. I was thinking about doing a whole video on one paper. Anyway, the events A and B are mutually exclusive. Well, this is just simply if the probability of A union B equals 0, then A and B are, which kind of makes sense, are mutually exclusive. And if we look up, they're clearly not. So, you know, so mutually exclusive, then, well, this is not the case. It actually equals a quarter, right? Which is not equal to 0. So they're not mutually exclusive. Cool. Right, let's keep this show on the road. I don't want it to be too long, but I feel like it might have to be. It's a goddamn good coffee. Right. let's read this survey. In this case, probably these people. Okay. Cool. So the only real new information here is this. So we know, so find x, we know that the probability that a randomly chosen person views the past photos fewer than 3 times is this. So randomly chosen but views of a photo, we'll just call that, this means views the photos less than 3 times, so just say that, is 0.801. And then it says find x. Well, the probability, so we'll just make sure we know what we're doing here. So the probability of a person viewing photos less than 3 times, we'll call that the probability. This equals the probability of less than 3 times. Well, that just means the probability is less than 3 times. Well, how many ways can that occur? Well, there's 2 ways. You can take fewer than 100 photos, and then you can view it fewer than 3 times. So this number here, because these have to equal 1, well, this number here is going to be 1 minus that, so 0.24. And the same goes with this one, so 0.1. And this is going to be x, 1 minus x, sorry. Let's erase that bad boy. So 1 minus x, because the total probability has to always equal 1. So you've got 2 ways of it being fewer than 3 times. It's you take fewer than 100 photos, and then you view it fewer than 3 times. Or you take at least 100 photos and view fewer than 3 times. You know, I'm stumbling my words, but you try to say that shit fast. So you got 2 different ways, basically. So this is going to equal to, well, the first way is x times 0.24. So that's 0.24x plus the way of doing it this way, which would be 1 minus x times 0.9. I hope that makes sense. So then you get, and this is clearly, this is so we get 0.801 equals 0.24x plus 0.90 minus 0.9x. Okay. So then we can just work that out. So brain. So we're going to have 0.801 minus 0.9. So this is minus 0.099 equals 0.24 minus 0.9 equals 9 equals minus 0.66x. Therefore, x equals minus 0.099 divided by answer. So this equals this. Oh, I hope I haven't been. I gotta remember that there's a webcam here. I completely forgot that. Oh well. Equals 0.15. Cool. Right, that's the answer. So that's I. And then I. Gotta remember not to go there, because you guys won't be able to see it. Given that a person... Oh, look, we gotta give them one here. So, given that a person views past photos at least 3 times. So, we'll say... find the probability that a person takes at least 100 photos. Okay, so we could go event A. Event A is equal to event A is equal to the probability that a person takes at least 100 photos. So takes at least 100 photos, and then B can be the probability that a person takes at least, sorry. So just a probability that is greater than or equal to 100 photos. And then B can be the probability that he views past photos at least 3 times. So this is views past photos at least. Views, yeah, we'll just say views photos 3. Okay, so it wants to know the conditional probability here. So that it wants to know what the probability of the probability that a person given, so A given B. So it wants to know, given that we view the photos at least 3 times, what is the probability that we took at least 100 photos? Well, this is going to be, like I said before, this over the probability of B. Right? And the probability of both of them occurring, well, let's go here. The probability of A union B is going to equal to, let's go to our graph. So the probability of A occurring and B occurring, so the probability of A, what's A again, is 100. So this, at least 100 photos, which was what? 1 minus x, and x is, so this is 1 minus x, which equals 1 minus 0.15. Oh, this doesn't equal. Fuck. Just doing a quick calculation on the side. Equals 0.85. So that's, yeah, fuck. I'll just get rid of this. I hope you know where this comes from. But the probability of A union B equals 1 minus 0.15, which is this probability here. And then we take at least views 3 times, so that's 0.1. So it's this times 0.1, so which is 0.85 times 0.1. Cool beans, which is 0.085. Right, and then the probability of B will be, the probability of B, I mean you could just do 1 minus 0.801, right? Because the probability of B is we view at least 3 photos, and then the probability that a randomly chosen person views past one or fewer, so that has to sum to 1. But you could do it the full way. I mean, you could also say, I mean, this is going to equal what? I should really do all these calculations beforehand. 0.199. I mean, you could do it like this and say, well, it's just, I'm taking way too long on this question. You could say it's just this. It'll be 0.85. It'd be equal to 0.85 times 0.1, which is 0.85 times 0.1, at least photos, and then 0.15 times 0.76 plus 0.15 times 0.76, and that should equal 0.199 as well. Look, whatever way you want to do it is whatever. So then your conditional probability of this is equal to 0.085 divided by 0.199, which equals 0.085 divided by 0.199, which equals to union B, which equals to 0.427 plus. Still not used to the pen. Cool, that's the answer. We took too long on that question. Okay, question 5. Right. The table shows the mean and standard deviation of turkeys. I do encourage people to try these before they watch this. Okay, let's go down a bit. Okay, I. Oh god. Okay, I. You know, this is a trial. It's not going perfect. The number of birds, so you've got a distribution here. I mean, not a distribution. You've got, you know, 9 turkeys with a mean of 7.1 and standard deviation 1.45, and geeses, 18 of those. So it says find the mean weight of 27 birds. That's the total birds. Well, we know that the mean, let's call it this actually. And this should be on your formula sheet, is, you know, the sum of all of the, I mean, it'd be I to I is an N. So it'd be the sum of all of the birds mean, so that'll be the total mean basically. So it'll be all the sum, so it'll be just 9 times 7.1 plus 18 times 5.2, right, divided by 27, which gives you plus 18 times 5.2 divided by 27. So it gives you 5.83. So we can call this the 5.83. So we can call this the mean overall. Overall equals 5.83. You know, so it's just the sum of all the means divided by the total number of birds, which gives you the mean of all the birds. It's not too shabby. I. The weight of individual turkeys are denoted by xt kilograms, xg, standard deviation of the weights of all the birds. Just to make sure my computer's plugged in. Okay. So we know from our formula sheet, which that the the variance is equal to the square, no, that's not right, is equal to the sum of x minus mu squared over n. So in this case we'll have a variance of the turkeys, which is the sum of x, and remember this is I, so it's all of the n of turkeys minus the mu. Wait, I guess it'd be better to use the other equation. I'm pretty sure they'll give you both. Wait, hold on, I'll just check. So if we scroll up here, okay, yeah. So this thing here, so this is the equation we're going to want to use. I could actually, I'll show you how they get from this one to this one. So we have this, and then this also equals, which is, you know, it's a jump. What was it again? X, okay, cool. X squared over n minus mu squared, right? And again, I don't have to keep writing that, but it's just important that you know it's summing over all of them. So that means that the standard the variance is going to equal, for the turkeys, is going to be the sum of xi squared over n of turkeys, so the number of turkeys, minus the mu of turkeys squared, which equals so we've got the mu of turkeys, the standard deviation is 1.5 squared, 0.5 squared, which equals xi squared over 9, it's 9, yep, minus 7.1 squared, 7.1 squared. So then if you work that out, so you've got 1.5 squared plus 7.1 squared times 9. So that gives you this. Because it gives you a hint in the question, it asks you to find these things. We'll call it for the turkeys. For the turkeys. Yeah, for the turkeys. Yeah, we'll call it T. This is how they called it. Equals, I got 472.6. Okay. And then you can do the same thing for the geese, which gives you xg squared over ng minus mu g squared, which gives you 0.96 squared equals the sum xg squared over, what was it, 18 and 5.2. 18 minus 5.2 squared, which if you do that calculation is 0.96 squared plus 5.2 squared times 28. It's 500. So this is equal to xg squared equals 503.3. Cool. So then the total variance is going to be, well, the sum of all of the things, which is just the sum of all the xg squares and the sum of all the xt squares. So xg squared plus sum of the xt squared over the total number, call it total, minus the total mean squared, or the overall mean, which we calculated in I. And that will equal to 503.3 plus 472.6 over 27 minus 5.83 squared. Pretty sure I did this one before. So maybe I didn't. Okay, I'll just calculate it. 503.3 plus 472.6 divided by 27 minus 5.83 squared. Square root answer. Plus 472.6 divided by 27 minus 5.83 squared. Squared answer. Okay, so I got 1 point. I'll do these calculations beforehand next time. Okay, so I got this. So the standard deviation overall, I got to be 1.4, what was it, 1.5? Oh, 1.2. 1.21. Cool. I actually want to show you, because I just saw that, up here, we made this assumption, which to me is not very clear why we can do that. Like from here to here, we can just say that. So I just want to maybe just show you why that is. So let's delete all this. And let's rub this stuff out. And then I'll show you where that comes from. Okay. So we've just assumed here that the sum of our from I to I equals n of our xi minus mu squared over n equals the sum, I'm not going to keep writing that I thing, xi squared over n minus mu squared. And well, let's show you why that is. So we have this here, sum of xi minus mu squared over n. Pretty sure we'll be able to find something here and be able to prove this for you. Minus mu. You know, don't just take things for what they are. You know, say why is that? You know, where does that come from? You know, do things like this. It's really good for you, good for your learning. So, I mean, we just expand this out. So we've got the sum of, it's going to be xi squared minus 2 mu xi plus mu squared all over n. I don't know if this is a little above this level, but whatever. And then that will equal, well, you can split these sums up over n minus the sum of 2 mu xi over n minus the sum of mu squared over n, which equals the sum of xi squared over n minus, well, the 2 mu is constant, so when you're summing it over, you can just take it out. It doesn't make any difference. Of xi over n minus, wait, that's a plus, sorry. This is a plus. Plus, well, the sum of a lot of mu squares from I, because this is, remember, this is I equals 1 to I equals n. So the sum of all of those mu squares is just going to be n mu squared. I hope you can see that. I mean, if you just sum up 10 mu squareds, you're just going to get 10 mu squareds. So then this, then this thing becomes, well, we'll keep that because that's what we want in the end. Minus, well, this is just the mean. So this becomes minus mu squared, and these cancel out, so you can see where this is going, plus mu squared. And therefore we get the variance squared equals this. Plus, minus 2 mu squared plus mu squared minus mu squared, which is what we had above. And we proved it from the other one. So we showed that this thing equals this thing right there. I thought that'd just be useful. Anyway, let's move on. How many more questions? We've got 2 more. I don't know how long this has been. Okay, question 6. Question 6 Aruni. 6 Aruni. Right. Okay. In a certain country, 68% of households have printers. Find the probability that in a random sample of 8 households... Okay, so this is just the binomial distribution. Because we have a success, a household has a printer, and we have a failure, a household does not have a printer. So, let's do that. So, and you can just go on your formula sheet and see that the probability for the binomial distribution is n. I wrote it down, x. I don't really like statistics at all. It's interesting. Statistics is interesting because, you know, it pops up a lot in the real world, which is really interesting. But I don't know. I'm not that huge of a fan. So the probability is just simply going to be. So the probability is just going to be the probability that. So we can say the probability total. I don't know. Probability total is going to. The probability that x equals 5 plus the probability that x equals 6 plus the probability that x equals 7, which is simply going to be 8, 5. So 8, pick 5, and the probability of success is 0.68. Again, if you don't know where this formula comes from, look it up and understand where it comes from. Understand where it comes from. Don't just use it. You know, it'll make your life so much easier. So the power of x, which is 5, and this is 3, plus 8, 6, 8 pick 6, 0.68, 6, 0.32, 2, plus, and then 8, 7, 0.68, 7, 0.32. And that'll just give you an answer of, I already looked, let's calculate this one. We'll give you an answer of 0.722. So that's the total probability. Cool. I. Use an approximation to find the probability that in a random sample of 500 houses or more, there's 337. Okay, cool. So in this case, we use the normal approx for the binomial distribution. Okay. Again, the reasons that we do that, you can look those up. I mean, there's a lot of reasons why we do that because, I mean, I can tell you a few. So when we can assume the mean is equal to n times p, which is the success, which in this case is 500, because it says n is 500 houses, times 0.68. And you can see how that could roughly be the mean. If you have 500 and you have a 0.68 chance of success, well, then on average, you're going to get 325 times 0.68, 340, you know, people with printers in their house. Okay, and then you can also see from the variance when you use a normal approximation for this binomial distribution is equal to np times p minus 1. And again, reasons for this you can look up. I feel like that's pretty obvious. Maybe this one not as much. And remember, just the variance is just a measure of the spread of the data. So in a normal distribution, how much it spreads. You know, the higher the variance, the higher the standard deviation, the higher the spread. And the reason that we actually use variance is because the squared always makes it a positive number. So even if you had a negative, and that's very useful for mathematicians to have things positive. Because even if you have a negative standard deviation, you still have a positive variance. So a lot of the time they graph the variance instead of the standard deviation. Anyway, so this is 500 times your probability of success is 0.68 times your probability of failure is 0.32, which is going to equal times 0.32 is 108.8. So it gives you a variance of 108.8. Now the reason that we can use this normal distribution for a normal approximation for the binomial distribution is because we have large values of n. Pretty much. I mean, your NP, I think it has to be greater than 10 or sometimes 5, depending on what textbook you're using. And if that's the case, then we can model a normal distribution over our binomial distribution. And I think the other one is NP minus 1 has to be greater than 10 as well, which in this case they both are. I mean, NP minus 1 is definitely greater than 10. They're both greater than 10. So we can use that. And again, look up why. Why can we use that shit? Anyway, so now we have a mean and a variance, and we want to find out the probability that a random is more than 337. So the probability that x is greater than 337. What is that? Well, let's look at our normal distribution, which we have approximated. That is terrible, Jake. That's just an awful distribution. Let's just try that shit again. Like that. There we go. So our mean is 340. And x here is 337. So we want the probability that it's greater. So we want this area here. And well, how do we do that? We find the z value. But in this case, when we approximate, that would be okay if we just found the z value for 337 minus the mean 340 divided by the square root of 108.8. That would be okay, but there's a better way of doing it. Because when we zoom in on this, and this comes from intuition, when you look at these approximations, if we zoom in, you can see, well, because it's a binomial distribution being approximated, then at 337 we want more than 337. So by saying that we want 337 included, because they're distinct values, unlike, you know, with a normal distribution which is continuous, you can't, the probability of 337 occurring, well, that's equal to 0, because it's impossible for that exact value to happen. You know, 337.000000000, you know, it's impossible for that one perfect value. But with a binomial distribution, it's discrete. It's either a success or it's a failure, and 337 successes is definitely possible. That's why you have these graphs, these bars here. So we actually want to find the probability of it being greater than 337.5, because that will exclude 337 from our calculation, which is what we want. If we count 337, then we're counting this extra little bit here, which we don't want at all. And if you don't understand that, well, you should look that up for the approximation as well. So in fact, we want to do this one, because it's a better approximation, 08.8, and that gives us a z value of 337.5 minus 340 divided by the square root of 108.8. This gives you a z value of negative 0.2397. Cool, and then from that, now we have a graph. From that, all we need to do is then, because the graph is symmetric, is find what this area is. 0.239. You know? So what is this? Well, you just go to your graph, and go to your table, and I think I already did this. But I didn't know if I wrote it down. I think it's 0.595. If that's wrong, I apologize, but that's what I wrote down. So you just go to your table and you plug this bad boy in, and you see what the probability of that z value occurring. And that answer right there, so the probability that z is greater than negative 0.2397 equals the probability that x is greater than 337, which equals 0.595. So that is your answer. Cool. Last one. We're on the home stretch. If you made it this far, you should give yourself a pat on the back. I hope this kind of stuff will be helpful, especially when I get out of statistics, because statistics is not my best thing. But I can still do it. Why do I need to write 7? Righto, so A. Okay, this is combinations and permutations. So we have this number 2, 2, 3, 6, 7, 7, 8, 8, 8. How many ways, different ways, can these 9 digits be arranged if there are no restrictions? Well, if there are no restrictions, let's think about it like this. If you had 1 to 9, and there were no double ups, well, it would just be 9 factorial. It would just be how many ways you can arrange 9 different things. And again, if you want the intuition behind that, you need to look it up. I mean, it makes sense. You pick, if you have 1, 2, 3, 4, 5, 6, 7, 8, 9 slots, and you have 1 to 9, well, there's 9 ways to pick the first one, there's 8 ways to pick the second one, 7 ways to pick the third one, and so on, all the way to 1, and that is just 9, 9 factorial ways. But in this case, we have double ups of 2, 7, and 8. So that means the total number of ways will be 9 factorial over the number of ways we can arrange these ones, divided by, because it doesn't matter if this 8's here and this 8's here, or this 8's here and this 8's here. We can arrange those 8's 3 factorial ways, we can arrange those 2's 2 factorial ways, and we can arrange those 7's 2 factorial ways. So we have to account for those doubling count, that we count too many times, we count too many times, so we have to divide by those different combinations of that 9-digit number. So the answer is this, and that is, again, I think, yeah, I did this, yeah, I jotted this one down. So the answer is then 100,080 ways, which is shitloads. If the number made is even. So immediately when I see that 1, 2, 3, 4, 5, 6, 7, 8, 9, I'm thinking this last number has to be even. And if it is, then the whole number is even, clearly. And what ways is that possible? Well, the ways it's possible, if it's a 2, if it's a 7, or a 6, or an 8. Well, let's look at the first way. So if it's a, and then it's a 2 at the end, well then how many ways can we arrange those last 8 numbers? Well, we just call it 8 factorial divided by, because again we have double ups, but we don't have double up of 2 now because we've used 1 for the even number. So it would be divided by 2 factorial times 3 factorial. Yeah? So 3 factorial, 2 factorial. And then we can look at what if we have blah 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 blah, and then a 6. Well, 6 only occurs once, so it's going to be the number of ways that we can arrange these 8 remaining numbers is 8 factorial divided by 3 factorial, 2 factorial, 2 factorial. And then finally, 8 on the end is 8 factorial. Well, you've taken one of the 8's out, so it's going to be 2 factorial times 2 factorial times 2 factorial. And then you just work these all out, put them in your calculator, add them together, and that gives you the total number of ways, which I calculated, which equals, this is 10,080 ways. This one is not that, and I can just work that out for you. So 9 factorial divided by 3 factorial times 2 factorial times 2 factorial. This is 15,000 and 120 ways. Sorry if I messed up a few of those calculations. But you get the general idea. The calculation part is the easiest part. Okay. Wait, is that it? No, okay, we've got one more. Okay, we got one more, so B. Sandra wishes to buy some applications. Smartphone only has enough money for 5 apps. 3 trains, 6 social, and 14 game apps available. She wants at least one of each type of the app. Find the number of different ways this is possible. Okay. Well, again, let's just... She can only afford... So she can only get, you know, dollar. She can only get 5 apps. And there was 3 train apps, 6, so 3, we'll call it T, 3 train apps, 6 social apps, and 14 game apps. So, and she has to have one of each. Well, how many different ways can she do that? So let's make some. This is how I do it. I put them in columns. I'd say, well, she can have. Let's just. These are the columns. You can have 1 train app, 1 social app, and 3 game app, which is 5. She could have 1 train app, 2 social apps, and 2 game apps. She could have 1 train app, 3 social apps, and 1 game app. Because these all include her having one of each at least. She could have 2 of those, 1 of those, and 2 of those. She could have 2 of those, 2 of those, and 1 of those. Is that all? 1, 2, 3, 4, 5. Oh no, you can still have 1 more, sorry. 3, 1, 1. And that's it, right? 6 different ways. And then all you do is you calculate for each one the ways, total number of ways she could pick. So for this one, the total number of ways she can pick from 3 train apps, 1 train app. Because remember, these are different apps. So it matters which one she picks, you know? Times the number of ways she can pick from 6 social apps, 1 of them. And times the number of ways that she can pick 3 game apps from 14. 3. And then you work out what that is, which is 6, 5, 5, 2. And you do the same for this one. 3C1 times, I hope this makes sense, C2. Understanding this, you should really go away and make sure you understand what it means for this to happen. Don't just plug it in your calculator. Khan Academy usually will do a good job of helping you out with that. I can too, but you know, time is limited. 2, so then we got 14C2, and that equals 4,095, and then this one is, I mean, you get the idea here, C1 times 6C3 times 14C1, and then you do that. I mean, you just do the same for all of these. You know, this would be 3C3 times 6C1 times 14C1, which equals 84. Yeah, and then what you do is you add all these different ways up together, and you get the total ways in which she can do this is equal to 13,839. And I hope those calculations are right, and I think that is the end of the paper. So we went through the whole paper, and my plan is now to continue to do more papers. I really want to do the physics ones and the more pure maths ones as well, because I much enjoy those, and hopefully I can then move on to A2 and maybe even university level papers. But for now, we'll just stick with the high school papers, and we'll keep banging these out. Thank you for watching, and peace out, boy.